All right, recording's rolling. It's Tuesday, May 3rd. That's finished the final exam review in my other classes, but you guys, first period, we've done this already, so we're going to go on to this stats page. You guys should each have one of these, right? You guys each got this? Right, didn't miss anybody? All right. Now, what's this about? Well, this is actually a segue into quantum mechanics. What I'm eventually going to do, probably a couple days, I'll give you guys this page. This is on Google Classroom already if you want a sneak preview. We're going to cover all these topics within quantum mechanics. But what is quantum mechanics? Quantum mechanics is the physics of really tiny things. We're talking about atoms, subatomic particles. When we get down that small, well, a lot of the physics that you guys have learned throughout this year sort of goes out the window, and you have to think differently. Things don't exist in discrete particles. Things adopt wave-like properties. Things exist probabilistically. So like, where is an electron? Exactly how fast is it moving? It's really more of a matter of probability than saying like, oh, it's exactly at this point, moving this fast, sort of thing. And so I think it is good to have at least some basic statistics background, so you can at least have some statistics concepts to work with, right? How many guys are in stats or have had stats? Who said statistics? Oh, nobody here? Oh, all right. So I'm going to take like a whole year of stuff and get the very important things out of it and crunch this down into just a couple of days for us. Thank you. Just real fast. Right, and we'll just make some progress on this. All my classes are a little out of sync, but I'm trying to get us all back together. So we might have 5 or 10 spare minutes today. Well, we'll see. Let's get us going, get the ball rolling. Right. All right. So, oh, no, we're good here. All right. So, you guys see there's 5 dogs, 5 people, and 5 trees. Is that all right? Now, get these a little bit out of order. I'm gonna start actually with this graphic over here. You guys see how there's frequency versus height? Is that? Ooh, and I see 3 bell curves. You guys see those bell curves? Right. Now you can check your numbers if you want. Everybody has a little bit different numbers. I made lots of different versions like I normally do. But what should be the case regardless is that you should have kind of short dogs, kind of medium people, and kind of tall trees. You guys got that? Right. And just from that, you can pick out which bell curve is which. See how it's increasing height to the right? What do you think the middle bell curve represents? What population? People. So go ahead and label that people or humans. Humans or people, one or the other. I'll figure it out. Okay. And why is it a bell curve? Well, actually, it comes from an aggregation of bar charts. So here, let me put a bunch of bars on here. So if I ask like, how many people in the world are, let's say like 5'8" or something, right? I might get a lot of people. That's probably pretty close to like an average height. I'm guessing like 5'8", right? Then I say, how many people are 5'9"? Probably like almost as many, but a few fewer people, right? How many people are 5'10" and 5'11"? And you can keep going on up. There's probably fewer and fewer people the higher you go. Hey, is there anybody out in the world who's like 6'10"? Is that a thing? Yeah, very, very few people. How many people out there are like 7'3"? Maybe like 5 people or something, right? So if I made a bar for that, that'd be like a very short bar, wouldn't it? And so that's increasing height going to the right. Now you could also go decreasing height. So how many people in the world are like 5'4" and 5'3" and 5'2"? And you can make a bar chart with this and be fewer and fewer people. And if we're talking about like grown adult people, okay? How many people in the world are like 4 foot even, like 4 foot? There's probably a couple, right? Right. So, all right. And then you get this bell curve distribution. You guys see where the bell curve's coming from? Right. All right. And do you think the average would be at the peak here? Like there'd be average mean or average median, either one, if it's a true normal distribution, right? They're like right there. Right. Right. How about let's switch over to dogs. Now, dogs compared to people. Do dogs have crazy variability in their heights? Get you checked in here. All right. So like, if you compare all the heights of people, I mean, people are sort of kind of the same height, 5-6 feet, like somewhere there, right? But dogs, man, you got medium-sized dogs, you got lots of Chihuahuas, you got lots of Great Danes. I mean, there's a huge variability for dogs that compared to people. Wouldn't that be true? Right? Label this left curve dogs. Right? Now it's to the left of people because dogs are shorter than people. Like the average dog is shorter than the average person. right? I said that's why it's to the left, right? It's more spread out because there's more variability, right? And as a consequence of being more spread out, it also happens to be shorter, right? It's not short because dogs are short. I should probably change this graph because that it's to the left of people because dogs are shorter. It's scrunched down as a consequence of it being spread out because the area under each one of these curves represents 100% of their respective population. So 100% of people are under the people curve. 100% of dogs under the dog curve. Oh, and this last one's obviously going to be trees, right? Right. So 100% of trees are under the tree curve, right? And if they each have the same area, they would just represent 100% of some population. Then if you spread it out, doesn't that, as a consequence, like make it shorter? Hey, you guys can see that, right? So let's switch over and look at the trees. So I gave you guys a list of trees that are all like almost exactly the same height. You guys see that? Now, maybe these are selected for trees. Maybe it's like, it's over at the local hardware store and they're selling trees for Christmas and they all want like the same like height Christmas tree. It's like, okay, well, we know this height sells the best. So we're going to sell all the same height tree, right? So we'll try to order them the same height. Maybe they won't get it exactly, but pretty close. The fact that there's such little variability, or back up a little bit, the fact that the trees are taller than people, that's why it's to the right. Yes, that. So greater height going to the right. Right. The fact that there's such very little variability, they're all like almost the same height. Are you gonna have a bell curve that's very skinny? Right. And because it's very skinny and it's 100% of the population area, it's also very tall as a consequence. Okay. But the to the right tells you tall trees, and the skinny part of it tells you very little variability. And those are the two most important aspects. Okay. All right. You guys good so far with how bell curves work? Okay. All right. So how can we attach some numbers to this? Okay. So I see big picture graphical how bell curves are working. Okay. Well, let's look at some numbers. Now, I gave you for each of these populations a sample of 5, and we're going to do something a little bit crazy, but we can actually do this. Well, sort of. We're going to assume that these 5 heights are somehow representative of like the entire population. You can extrapolate out of it and say, okay, it's going to be like the average of these 5 is the average of the population, the whole deal. Right? So there's 2 boxes. What's the mean and what's the standard deviation? Let's start with the mean. I'll talk about standard deviation here in a few minutes, but with the mean, I bet everybody in here can calculate the mean. You guys have been probably doing this since elementary school. Can you just add up the 5 numbers and divide by 5? Right? Yeah, let's do that right here. You guys got a calculator up? So open parenthesis. I've got these 5 dogs. This guy plus this guy plus this guy plus this guy plus this guy. Close parenthesis, divide by 5. And my average height is this many centimeters. Mine happens to be a whole number. Yours may or may not be a whole number. So if it doesn't, if you get a decimal, keep at least 1 decimal place for this next thing that we're about to do. Okay. And if you do it right, then your mean height should be kind of the middle-ish of the numbers, right? Like you should get some dogs that are shorter and some dogs that are taller. It should be kind of in the middle. Okay, you guys got that? All right. Good so far? Okay, now standard deviation. Standard deviation is a statistical way to measure the spread of the data. Remember I was saying like these bell curves, like some of them are spread out like the dogs and some of them are really like squished and like the trees, right? To tell something about variability, right? There's a way to measure that. And I'll show you guys graphically exactly what the standard deviation is referring to. Okay? So let's go back to these bell curves. Right? Do you guys see how like the middle of the bell curve looks like an upside down bowl, but the tails look like a right side up bowl? You guys see that? There's some point where it switches over from being upside down to right side up, right? Probably right about here and here, I'm gonna say, right? Go ahead and put a point there just to make it visual, right? Do you see where it switches from concave down to concave up, right? Concavity switches, right? Guys, what's the name of that point where the concavity switches? I bet at least a couple of guys are in calculus and actually might know this. It's called an inflection point, right? Yeah, that's what you're thinking. Inflection point, IPE, inflection point, right? And if you go from the mean, which is like right here, to that inflection point, like this distance, right? Do you think that distance tells you something about how the data in general is spread, like how spread out it is? Like for dogs, that distance would be pretty big. For people, it's kind of like a Goldilocks, like medium, right? And for trees, it'd be like a tiny, tiny distance, right? That distance is called one standard deviation. I'm going to use Greek letter sigma to represent that, but you can also use the lowercase letter s. I'll use those interchangeably. They're technically slightly different things, but again, broad brush, skipping over some things, some details. Just looking broad concepts here, right? Okay, that's one standard deviation, right? Now, what I'll eventually get in more like tomorrow type stuff is that if you guys see how it's kind of a plus or minus factor. If you go one standard deviation above and one standard deviation below the mean, see how that would be that much of the bell curve? You see that? Now, there's a rule in stats that if you have data that is normally distributed, that right there represents 68% of the population. So 68%, that's pretty close to 2/3, right? So close to 2/3 of people are one standard deviation above or below the mean. And then you got like about 1/6 of people that are super tall and about 1/6 of people that are super short. Okay, let's say like beyond one standard deviation on either tail. Okay, you guys see that? Right. So we're going to say that for tomorrow though. But right now we're going to figure out how do you calculate that standard deviation, right, in some number of centimeters, right? Same unit. Well, I got a formula for it right here. All right, so what does this say? Let me zoom in where you guys can see this. All right, I'll step you guys through step by step. This is going to be a process. Okay, it's going to be a process. You guys see x sub I? That refers to an individual data point. We each have 5, right? It's like 5 dogs, 5 people, five something. I'm going to subtract the mean from each one, take a difference. Now the difference might be positive or negative, but that's going to end up not mattering because we're going to square it. See, whenever you square something, you lose the positive or negative information, right? Great. Then what does that capital sigma mean to do? Add them up, right? So we're going to add up the squares of the differences for each of the 5 samples, right? Then we're going to divide by n-1. N refers to the population size. So the fact that you have 5 dogs, we're going to do 5 minus 1 is 4. Now the -1, there's a whole conversation behind that. I'm going to skip. It has to do with like degrees of freedom. If you take stats one day, you can learn that from your stats teacher. But for today, we're just going to run with it. Okay. So we're going to do divide by 5 minus 1. So that's divide by 4. Then finally, we're going to take the square root. And that is a way, you can get this right here. That's exactly how many centimeters that is. Okay. So let me pull up a paper and do this with you guys. Okay. So just for completion for the video, I'll do X bar, the average was, my dogs are 85 centimeters, 87 centimeters, 98 centimeters, 112 centimeters, 123 centimeters. We got to divide by my 5 dogs. And I got 101 centimeter average. So that's my X bar, my average value. Okay, so that was the answer to the first box. Okay. Now I'm going to move on to the second box. All right, you guys ready for this whole process? Here we go. So standard deviation is, so call it sigma. You can also say S is fine. Okay. So I'm going to take each dog, subtract the mean. So for me, that'd be this minus this. So I'm going to go 85 minus 101 centimeters, square that, add that to 87 minus 101, square that, add that to 98 minus 101, square that, add that to 112 minus 101, square that, add that to 123 minus 101, and square that. Okay. Then take all this fun stuff, divide by, remember how there were 5 dogs? So I'm going to go 5 minus 1 for degrees of freedom. Okay. Then take all that, and I'm going to square root it. Okay. And that right there is standard deviation, which again is a measure of how spread out is your data, right? Like if they were all exactly, or sorry, am I doing dogs? Yeah, dogs, right? Okay. If all dogs were exactly uniform, the same, then subtract, you just get 0 up here. So the answer would be 0 if everything was like printed out like from a cookie cutter machine. Okay. But in nature, things aren't cut out from a cookie cutter machine. So there's some variability, and that's how we can measure this. So I'll do this on my calculator while you guys are doing this in your calculator for your numbers. All right. And I'm getting a number. And that number is the answer to this box. You guys good so far? That's right. All right. This is all being recorded. I'm gonna post this to Google Classroom, like probably here in about 5 minutes. So, all right. Now, remember what this means. Right? Your average dog, 101 centimeters tall. If you do plus or minus about 16 centimeters, that should cover about 2/3 of all dogs, right? Okay. All right. Now, we just did this the long way. We did it all on paper, every step by step by step. Right? But there's a fast way to do this. If you have this model calculator, do you guys find this model calculator lying around? Right. So find one that looks like this. Right. Right. Doesn't have to be green, but it says TI 30 X2S. You guys got that? Right. Let's do this. Hit second and then see stat var. So like exit stat. There. So some of these are probably programmed already. So hit second, exit stat, and see where it says yes. Hit yes. We're just going to clear out the data from last classes because we've been doing this all day. Okay. All right. Okay. Now you guys got that? You guys got a clear calculator? Or if you like, there's a button on the back that says reset. You hit that. All right. One way or another. Got to clear it. All right. Now let's do this. Hit second stat. There's a button that says data on it, but right above it says stat. You guys hit that, right? You guys hit that. It should say one variable. You guys see one variable? Okay. All right. Everybody good? All right. Hit enter. If you get lost, raise your hand. Let me know. Right. Then there should pop up a little word on our screen that says stat. You guys see stat? Right. All good. Now hit the button that says data. You guys see data? Boink. Okay. X1. Ooh, this sounds like my first dog. I'm gonna pop in my first dog. He's 85 centimeters tall. Guys, type in your first dog. Everybody good? Then scroll down. Frequency 1. Oh yeah, there is one dog. Now if you had like, say you did a poll or population of like thousands, you might have said, oh, I've got 225 dogs. No, we've just got one dog. So we're good there. Scroll down again. X2. Hey, that's my second dog. He's this tall. Scroll down, scroll down. X3, that's my third dog. Scroll down, type in my fourth dog. Scroll down, and X5, and I type in my last dog. And then there's one of those, so plug in. Okay. You guys got your 5 dogs plug in? You guys got that? Okay. Who's got a question? We good? All right, now, you guys see the button that says stat var? You guys see stat var? Click that, boink, and it will calculate, and it tells you N is 5. Yep, so we got 5 dogs. Scroll to the right, X bar. Oh, hey, look at that. That's my average. Look at that. Average height. Scroll to the right again. Hey, there's a standard deviation. Right now, I've been calling this sigma. It says S. There's technically a difference between these two. We're gonna go with S. Okay. So long story short, we go with S. First a sample. Yep, it's 3:30. So let's call that a pause point. That's all right. We're doing pretty good, and we'll continue this adventure tomorrow.